First thing is to just understand, and we've mentioned some of these, but just so that we're all on the same page, sort of what is required from our storage layer. We want it to be highly performant. We want the performance to be across the data center network to be the same as it would be if it was local. To be able to go and say we don't need local anymore, it's really got to provide that kind of performance level. It's got to scale to data center size. It's got to be well integrated. Josh mentioned some of the integration points, but essentially the easiest way to integrate, first of all, is to make it a block storage layer. And then you can put whatever file system you want on top of that, or you can put whatever database you want on top of that. Block is a common building block for all. It's got to be flexible. If you want to bring it in as a software layer and you don't want to tie down, the whole point of doing software is you don't want to tie down to a specific piece of hardware. So you've got to be able to use different types of servers, different types of drives, different storage media types in that sense. You're going to be able to integrate them. They have different characteristics, maybe different performance levels, and you've got to be able to go and generate logical volumes that will be able to provide those characteristics to the applications in the appropriate way. You don't want to be using high performance drives for an application that doesn't need them, or vice versa. Efficiency we mentioned, ubiquitous access is critical. You want to be able to access anything from anywhere. That goes together with this, of course. And again, ease of use. Part of that is, again, integration with orchestration layers, so that you can use containers, you can use your VMs if you want to. You can provision things easily, programmatically, so that they're operationally efficient. Okay, what are our components? So we have 3.5 major components within our product. We have our centralized management, which is the one where it does all the aggregation and logical provisioning of things. This is the one which you can connect to with your orchestration. You can do the provisioning there. We have our client-side driver, which is the one that actually provides the interface into the block storage layer. This is what sits instead of your local device. Instead of your driver for your local device, you put in our driver instead, and it makes the storage appear local, even though it may be implemented remotely. This is really where all the intelligence resides, and this is one of the major architectural differences between our solution and other solutions. Most solutions, they implement any storage services on the target side where the drives are actually sitting. We are doing something else. We are implementing the storage services on the client side so that the application that wants to access the storage is providing the CPU required. And on the target side, we have our NVMesh target module, and we have a cluster manager which handles making the drives available to the clients, but it's not in the data path. Our RDDA technology allows us to run a RDMA, send out an RDMA network request, and it goes through the RDMA NICs, and when it hits this RDMA NIC, instead of going into a software layer here for the data path, it actually circumvents it and goes directly into the NVMe drive. And we'll go into more detail on that later, but this RDDA, the ability to go around the CPU for the implementation of the data path, is the most critical feature within our product today.
So that's how you get to say no CPU usage then, because
Exactly.
You're using it.
No CPU usage.
My client CPU
side.
is using it.
We are using.
But the target, okay.
By not using any target side CPU usage, I can work in a converged model, because if I'm running on machine A, I'm running my application A, and I'm serving out storage for some remote client, some remote application B. If I were using server CPU here, then application A would be hindered by it. I'd done my resourcing, and I said application A needs a 4-core CPU with 128 gigabytes of memory or whatever. And now if I was serving out storage from here in a converged mode, maybe that application isn't getting the 4 cores it was supposed to be getting. But by not requiring target side CPU, I can do that. I can now go schedule my application and know that it's not going to be hindered. It's not going to be, it's not going to have a noisy neighbor get in its way.
What is the target module? Is that the control path there?
It sets up the connections for the RDDA.
So that's control, okay.
It's a control layer, exactly. And the cluster manager is also a control layer for making sure that if something does go wrong, if a node goes down, if a drive goes down, then we can overcome that failure and continue to provide storage
So that
service.
takes CPU, but just not much.
It does, exactly. The control layer does take CPU, but the bulk of the CPU that you would use would be for the data layer. And that's why the RDDA is so effective.
And look, it's the first software-defined storage system that aligns to software-defined networking and separating the data plane and the control plane at all.
It's an interesting, it's a timely topic.
That's a very,
Well, just
very
based
good
on
point.
the conversation at the last.
Yeah.
Yeah, is the RNIC a standard NIC card, RDMA?
Yes, it's a standard RDMA NIC that was developed before we started. And currently, the majority of the RDMA NICs in the world are Mellanox NICs. Our software can run on a QLogic NIC as well, if needed. We are working with other vendors, other very large network vendors that are coming out to market with RDMA
The client
NICs
driver
throughout the
runs
year.
on Linux.
Currently, our software is Linux only.
Are you doing anything in terms of joint engineering with the likes of HPE's machine project, which uses photonics to do something similar?
At the moment, we're not.
Or are you more competing platforms?
We're not really competing. We're really based on Ethernet today. For the most part, you can run us on an InfiniBand layer. And in addition, as additional forms of RDMA come out, we will support them as well. Okay. Slightly deeper dive into the components and why they provide the attributes that we believe that they do. So our centralized management is a Node.js application. It runs on top of a MongoDB database. It's the one that pools the drives, provides a management layer. It pools the drives, and on top of it, you can provision volumes, and you can monitor what's going on. There's a GUI attached to it, so you have a single pane of glass in order to view what's going on in the system. But for the most part, you will use a RESTful API in order to seamlessly integrate it with your operations level. If you're running at a very large scale, thousands of nodes, tens of thousands of volumes, if you're running containers, maybe even hundreds of thousands of volumes, you don't want to be manually setting those things up. You want to have that going on dynamically. The service itself is built is using Node.js, which is stateless, and underneath a MongoDB that can scale. And in that way, it becomes a scale-out service of its own, which is what enables it to really scale to a data center scale. It's easy to provision the service logical volumes. We have inside the management, we provide policy-driven provisioning methods. So you can go and you can aggregate high-performance drives into a pool of high-performance drives. You can generate drives with high write endurance. And then you can go and you can provision them to certain applications depending upon what kind of storage needs they have. That simplified policy-based provisioning is what really makes it easy to have a large data center, lots and lots of variants or mixes of drives, and be able to use them for different applications efficiently. So I won't be using my low-end drives for my database and using my high-end drives for a VOD application that doesn't need to do a lot of writing into them. Any questions on this?
We're going to talk about how you build volumes later, right?
Yes.
And we're talking about, this has to be NVMe connected drives, period.
We are heavily optimized for NVMe. RDDA works only with NVMe drives.
Okay.
But we can manage other types of drives. But when you work in a converged mode, you will not get the benefits of RDDA.
Right.
So you will use some target side CPU for the data path.
If that's what you want, that's fine.
Yes.
Good.
Any plans to use NVDIMMs as well going forward?
We're not using NVDIMMs at the moment. We have plans for using other forms of non-volatile memory. Specifically, NVDIMMs are not something that we have a concrete plan for incorporating.
I'd add to that, though, we support anything that has a block device entry in Linux or something that supports an NVMe interface. So we are already, as soon as the Intel Optane drives come out with 3D XPoint, we're ready to go, we're ready to use them.
Yeah, good point, thank you.
The thought of using your software with spinning disks offends me.
So you could.
Offends us too.
You could. You wouldn't get the best performance out of it. We haven't done the tuning for the rotation of the drives. This really is a flash-oriented solution.
Makes sense.
Okay. Our block driver, and this is really where most of the magic, so to speak, happens. So it's as mentioned before, it's a kernel module that presents logical volumes as block devices. They look like a local drive. From any applications perspective, it just thinks that it's a local drive. But in fact, under the hood, it implements a more complex logical volume. As mentioned before, the client side is where all the storage services are implemented. And that's another key to enable convergence. If you're going to implement the storage services on the target side, you're going to need some CPU. If you're taking CPU, you can't work well in a converged mode because applications and storage will conflict with each other. How do we interact with the drives? So we're using RDDA, and I'll take this to maybe do a little bit of a deeper dive into how RDDA works. I will mention at the same time that there is a alternative to RDDA coming out, or another kind of transport protocol. We developed RDDA a few years ago when there was nothing else in the market. NVMe over fabrics is a standard that's been recently defined, And when devices come out that support this transport, our product is already NVMe over Fabrics ready. We have integrated with some companies that are building such devices.
So as a consumer, that you'll consume.
Exactly.
Okay.
We will consume them, but we will consume them and still do logical volumes on top of them. So if you
Right.
have multiple NVMe over Fabric drives, you'll be able to do a RAID 10 kind of implementation on
Okay.
top of them.
And are you? What's the state of support for NVMe over Fabric as a target, as a provider, not a consumer?
So we're not exposing NVMe over Fabrics. You can integrate the standard kernel NVMe over Fabrics target drive on top of our volumes. We've
Okay.
actually done that with some customers who wanted to integrate
So-
Windows, for instance, with us. But we don't see a huge amount of value in that. We are by exposing ourselves as a local volume and doing all the sharing, you don't necessarily need that.
People hate clients, and it's a way to avoid the client.
That's true. It's a proxy method. It's a good
Yeah.
way of doing things. But you could do it with an iSCSI target as well, for instance.
I'm going to assume that there'll be a bigger performance hit.
You will definitely see better performance with NVMe Fabrics. RDDA. So just in a nutshell, how does the magic sort of happen? I'm not going to go into all the bits and details of it, but in general, what we are doing is we're using RDMA write. We're sending out an RDMA write, whether we're performing a read or a write over RDDA, we send out a single RDMA write from the client side to the machine that has the NVMe drive in it. When that RDMA write is written, it has a few pieces in it. The first piece is something that is written into the NVMe drive's submission queue. The submission queue is where you tell it what to do. So basically, we're doing a remote write into the memory area of the NVMe drive where it accepts commands. The next thing that we do is we go and we write into the remote NICs queue a message to be sent back to us. It's sort of like sending a return. It's like sort of like sending out a survey with an envelope. There's already stamped envelope where somebody can fill out the survey and send it back to you. So
Handshake.
we're actually installing a message to be sent back to us from the target side. So we're putting it in the memory there.
Is that something like that interrupt that NVMe does? You send in a request for, is it called MSIX or something like that?
Exactly. So I'll come to that in a moment, how we use that.
Okay.
But first thing we do is we go and we put the NVMe element inside its queue. If there's any data that needs to be written into the drive, we'll also put that into the remote memory, and the NVMe command will reference that remote memory. Once we've put that envelope that can be sent back to us, we go and we do another write. It's all part of the same RDMA write, but the last piece of it is to go and ring the doorbell on the NVMe drive. Mm-hmm. So at this point, we have not used any target side software, and we've made by ringing the doorbell, now the NVMe drive starts to act. If we were doing a write, it will read the data from memory that we've installed, that we've already put there, and write it into the drive. If we're reading from the drive, it will at this point fill out a memory buffer that we've prepared beforehand, something that we call a bounce buffer, and we'll fill out that data. When it completes, when the NVMe operation completes, it will generate two things. It will generate a small completion, and it will send out an MSIX interrupt.
Right, cool.
MSIX interrupts, 99.999, probably 5 nines after that, of the interrupts ever generated are targeted at CPUs. That's the mechanism that they were defined to do. But luckily for us, whoever invented MSIX did a pretty good job because they made it more generic. It can write into anywhere you want in memory. And what we've done is we've pre-programmed the MSIX. Instead of going into a CPU, we've pre-programmed it to go and ring the doorbell on the NIC. So that envelope that we had prepared beforehand, it actually points to the completion queue on the NVMe queue that says what happened when we asked the NVMe to happen. And if we're reading data, it also points to that data. And so when the MSIX interrupt happens, it immediately rings the doorbell on the NIC, and the NIC will then send automatically, without again requiring any software, it will send back a message to us, which includes a completion queue entry and any relevant data. So that's just roughly how RDDA works. Of course, in the implementation, there's a lot of details that I'm not including, but this is our patented technology, and that's what really allows us to avoid any using target site CPU.
Okay.
Does that answer the question, I hope?
You
Is
hacked
there?
the server.
Sorry?
You hacked around the CPU.
We hacked around the CPU. That's the way of looking at it. I think we worked around the CPU.
And Intel provides the necessary plumbing for the RNIC is on a set of PCIe channels on processor A, but the NVMe card that I'm accessing is on processor B's channels?
So they can both be on the same processor. They can be on different processors. The Intel processors know how to
But Intel
route
takes
any
care of that
PCI
for you.
messaging.
Okay.
It works in either
And-
mode. It
and-
works on a multi-CPU system as
An
well.
immeasurable performance difference.
Yes.
say.
Compared to working through software, you save a lot of latency.
Oh, yeah.
And you save CPU cycles. That's the most important part of it.
So is a LUN assigned to an NVMe drive, if such a thing exists?
No, I guess we're gonna get
No,
there.
what we're providing are logical volumes. And
So does a logical volume apply to a specific NVMe drive?
no, a logical volume from our perspective is what we're calling a RAIN data protected volume. It doesn't have to have protection. You can choose to have just a highly performant non-protected volume, but a volume basically consists of one or more partial drives. So I can go and say I need a very, very high performance volume. I want to get the performance of several drives aggregated, but I don't need a lot of space. So I'll ask and I'll go and I'll configure what we call a RAID 0. A RAID 0 across multiple drives so I can get the joint performance of them, and I'll just take a little slice from each one of them. Alternatively, I may need a very large drive. I may need all the performance, but I need the capacity. So I'll go and aggregate multiple drives, larger drives, and incorporate the entire drive. The logical LUN is associated with a whole bunch of drives potentially, and it could be just part of one drive. What we are implementing for data protection, we're implementing what's called a RAIN sometimes. It's like a RAID, except that it's across nodes, not across drives in the same machine. So if a machine fails, I can still access the data from another machine. In fact, together with our policy-based provisioning, you can go and say, I actually want to separate the data to different racks within my data center. So if there's a rack failure, a power failure on a rack for some reason, if a Bobcat runs into a rack for some reason or other, I've still protected.
So you just
Something, forklift or something of the
That's
sort.
like you're actually coding with failure domains.
Yes, exactly.
so but your failure domains. I mean, you're going to be using at the client side is where its protection is going to get deployed.
Yes.
So are you able to do things like erasure coding or replication of data multiple times? How you do?
So in our current version, we're supporting RAID 10 essentially, or RAIN 10. We have erasure coding coming in one of our upcoming versions. It's later this year.
And all the CPUs required to do that. CPU cycles come from the client side,
Exactly.
as if it were a local, same as if it were a local.
Exactly.
Are you like
Brilliant.
at any point saturate the processing power on the NICs
Brilliant.
themselves?
You're distributing.
Potentially,
So-
could that be a bottleneck?
Yes.
Across the server.
Josh will be showing a demo later where we achieve millions of IOPS from a single box. And the limit there is really the NIC processing capability. But it's at millions of IOPS. So it gives you a lot of headway, a lot of room. But yes, in practice, it may be the bottleneck. It really depends on your balance between hardware. It depends on how many drives you put in and how many network NICs you put in. If you wanted to increase it, you could put in more NICs. Okay, so as I mentioned, most of the intelligence is in the client side. We do have a target side. The target side is mainly acting as a control path. If we're managing non-NVMe drives, it will also be part of the data path. The kernel mod, this is basically a kernel model also. It accepts clients' connections and sets up RDDA as appropriate. Again, RDDA means that the target module is not in the data path for NVMe drives. Nodes can run applications, serve storage without CPU conflict. Josh will show that we can serve millions of IOPS from a single target, get tens of gigabytes, and this is all off standard servers. There's no complex, specialized hardware that has been built specifically for this task. This is a standard server that you can go and buy for regular purposes, put in enough drives, put in some NICs, and you're set to go. Another point is scalability, and this is true for all our components. We don't use any broadcasts. We don't use any multicast. It's all point-to-point communication, and the relevance or the fan-out of the communication is always such only for the areas that are relevant for implementing the logical volume on the client or for logical volumes that are connected between different targets. And that's what really allows us to scale out to data center scale, our communication pattern, so to speak. We have another component that's called the Topology Manager. I call it a half a component in a sense because our Topology Manager and our target always work together. From the end user's perspective, it looks like a single service, but internally we differentiate between the two of them. The Topology Manager, in contrast to the target itself, runs in user space and it performs cluster management of sorts. It runs a multi-RAF protocol, which is an enhanced version of Paxos for those familiar with that. It's really what ensures that even though we're sharing a logical volume that can be spread across multiple nodes and multiple drives, We can ensure that we avoid any split brains and that data is consistently written into them. That's why you can run a GPFS or a Lustre file system or a CXFS shared file system or a database that has underlying shared storage without enduring any data corruption, of course. Again, here we have point-to-point communication between the management and the clients and the TOMAs, or our cluster managers, our topology managers, but also between themselves. We're not using a single RAF protocol across the entire data center. That would be very prohibitive for scaling. Instead, we are running multiple small rafts, which is again a differentiator between us and what the other software-defined storages that we know of are doing, and that's what allows us to scale. Any questions on this?
Two questions, but I think I understand the first one. The second one would be, what happens when a drive fails? How's that detected? Is it detected at the cluster manager or at the client? And what's the recovery aspect of that? And how does that go about?
Okay, so the cluster manager interacts with the target module that is running on the same machine. The target manager will receive an indication immediately that the drive is down. If it fails, it will usually spew out some kind of error, either at the PCI level if the drive is actually physically pulled out or has some physical problem, or it will receive error messages that something has gone wrong on the drive. It reacts to that and it basically goes up and says to the topology manager, hey, there's a problem with my drive. The topology manager will then be in touch using the RAF protocol with the other elements that are implementing the relevant logical volume, the elements that are in the same protection domain as that drive, any volumes that have shared segments with that drive, and it will take the steps required to go and tell the clients, hey, there's a failed drive here, this is how we're going to work around it. I said a lot very fast, I apologize.
No. And so the re-replication of the data and all that stuff is done at the client level or at the cluster manager level?
Right. So I didn't answer that part of the question, you're right. The identification of the error happens that way. When the drive, let's say I pulled out a drive. When I push it back in, maybe on an alternative server, then the target will recognize it being inserted. It will tell the topology manager. The topology manager will go and ask the management, hey, which volumes are running on this drive? And when it figures that out, it will go and say, hey, that drive that was out for a while, it's now back in. It will contact the relevant other topology managers that have the protected data, and it will initiate a recovery. A client can also do the recovery in parallel to speed up the process. So the recovery happens essentially on the target side, the rebuilding of any missed data. There are dirty bits, so to speak, like there are in other environments, so that the rebuild will occur fast and all that. But the recovery is managed by the topology managers. They will run it at a slow speed on the targets in order to ensure that it happens in a timely fashion. But the clients can also do recovery in parallel to speed things up if they need the data faster.
But the target doing the recovery does use CPU?
Absolutely, yes.
So
it will.
the topology manager is part of the cluster manager process.
The topology manager is the one implementing the cluster management.
Okay.
From our perspective, yeah.
And that means that we need HA for it, because while it's not actively in the data path, it's in the recovery path.
It is, and every one of our targets has its own topology manager with it.
Okay,
so it's very scalable.
So the Node.js cluster manager can die.
Yes.
And it only affects provisioning, not operation.
Right.
Yeah, you might want to say our Node.js node, the management node, is not actually the cluster manager. It's more a configuration database.
Okay.
And a monitoring station. It's not in the data path.
Yeah, I know. I saw it wasn't in the data path, but we started.
You just got up a break point. So the topology manager is something that can die and it can come back up. It's a recoverable process.
The configuration management GUI and RESTful interface can die, and the cluster keeps working.
I'm talking about the part that can detect the drive failure and do all the great stuff there on the server side.
Yeah, that's
if that's
distributed.
down and then the drive dies while that's down, are you in deep trouble?
No, you're not. When it comes back up, it will recover. Once that topology manager dies, its peers will recognize that it has died. It will be interpreted as a whole node being down, and all the drives within that node will essentially be considered down for
the whole node is evicted.
Yes, temporarily. And if the topology manager comes back up, things are rebuilt very fast.
That's good.
The management layer, while it's not critical for the control path, when you look at a data center environment, if you're running containers dynamically, you want that up all the time. You essentially, that's why we built it to be
if it's
highly available.
if it's a dynamic enough environment, you're provisioning all the time.
And that's what you'll find. That's what you'll find in practice. I keep pointing in the wrong direction. We mentioned earlier, our product lends itself very well to the converged model, where you run the target module and the cluster manager with it, and the client block driver on the compute nodes themselves. You sprinkle your storage devices within your compute nodes, and you can get the highest performance. Essentially, you're getting a virtual SAN that's not taking any rack space, and you're getting huge performance out of it. Alternatively, there are data center operators that prefer to disaggregate their storage and their compute physically. When our product can be deployed in that manner as well. If you go for very dense servers, we can get very high performance out of them. And again, that's something that Josh is going to go and show in the demo.
And those storage nodes could have dinky little processors.
They could have dinky little processors, exactly. That's one of the benefits, but they are standard servers.
The RNICs are a different story.
Yeah, but a Xeon D would make perfect sense for those storage nodes.
Yes.
You know, a lot of stuff on chip. 8 cores is plenty because you're only using it for rebuild and management.
And that's in the demo that Josh is going to show. He's using processors that cost us $250, $300. We're a startup. We don't have a lot of money for hardware. So those are the processors that we buy for our target.
Call David.
We do need PCIe lanes.
Yeah.
So oftentimes the really low-end processors, they really trim the number of PCIe lanes.
Yeah, but
Can you paint a picture for us of what a deployment would look like? Customer buys a couple of Dell servers, throws a couple of PCIe NVMe
Yes,
cards
we
in it,
can.
and
We'll do that in the demo, I think,
the
coming up.
Mellanox.
We're coming up pretty shortly. We're going
In
to
a
show
moment, I'll show that in
a
the
very
demo.
real-world
Let's
demo
steal
for
his
you.
thunder. Final word on this, you can run in a mixed mode as well. If you want to get the performance levels of converged storage, but you don't know how much storage you actually want to get, you don't want to overbuy, so you can buy what you consider to be the minimum amount that you will need and enjoy the performance levels attainable through a converged mode, and then you can bulk it up with additional disaggregated storage if you find that the resources that you have are insufficient. Okay. Performance, and Josh is really going to show this in a probably more convincing way through a demo, but I'll just mention what we get asked by customers. So the first thing they want to do is they say, okay, you're talking about remote access to storage. Can you really hit those numbers? Can I see the difference? Will my application see the difference between remote and local? So we've shown time and again that you can get the same level of IOPS for your application, whether you do it remotely or locally. You can get the same levels of bandwidth. You cannot get the same levels of latency. There's no way of working around the fact that you do have to go to the network. So going to the drive through RDDA does incur the network overhead. It's typically in the 4 to 6 millisecond range. Again, Josh will show that in the demo. For most applications, that's the
Microsecond.
Yeah. What did I say?
you said millisecond. You're only off by 3 orders of magnitude.
Only by a factor of 1,000. I apologize for that.
What are a couple orders of magnitude between friends? Come on.
We've been able to show that with a capacity optimized platform, something that you would use for disaggregated storage, there's no single server application that would need 5 million IOPS, but you can serve that out from a single server, standard server, almost 5 million IOPS, over 20 gigabytes per second of storage, all at latencies that are still in the same range as you would get when you do a single IO at a time, sub 200 microseconds. The next thing is showing scale. Josh will describe later on how we're being used at NASA, but they've been able to do over 140 gigabytes per second on a routine manner with 128 servers with a single NVMe device in each one in a converged mode. And that's roughly linear with the performance of a single drive. And true convergence, I think we've mentioned this, RDDA doesn't require any target site CPU usage. Hopefully that's clear by this point. We can literally get to over 100 million IOPS in a single rack. Not that you would necessarily want to, but you've got that headroom available if you need to. Key takeaways. We're a software-defined block storage solution. We're using standard servers. You can bring in state-of-the-art, the best-of-breed components, and really maximize the benefit you can get from them. We're providing what looks like a virtual SAN. We have an initial set of storage services. We're bulking it out as we go. They're built for NVMe and they leverage the NVMe capabilities. They make all data look local, essentially. You don't really care where your data actually is. You can put your compute wherever you want and it will be able to access the data. It can scale out. Our communications pattern, our information dissemination is such that we can scale out to practically any level. We're getting some pretty high targets from some of our customers. And so we really need to be able to scale out to those levels. No noisy neighbors, If your neighbor is using your devices, you don't feel it. Why? Because we've got this RDDA technology.